You could put in 2 batteries in a row, 3 batteries. You could put anything you want, or you can have, as you made in the lab, a power supply, which is a voltage supply. You can dial the voltage you want continuously. And all I'm saying is that if I start out with electrons, the question is, can they get across if there's an opposing voltage due to my battery or power supply? If the voltage is low enough and the kinetic energy is high enough, the voltage is low, like this one, and the kinetic energy is high enough, it can get across because it has some residual kinetic energy. It's being retarded by the field, but it has enough kinetic energy to get across. It's sort of like, again, a particle rolling up a hill, up a plank, say, onto a plateau, onto a table. If I have enough speed, I can roll up the plank, roll onto the table, and keep going, because I lose speed as I go up. So that's what's happening here. There's a retarding, just as there's a retarding gravity field that's preventing me from rolling up here, there's a retarding electric field preventing the electron from going across. No, I'm using this as a kind of part of my equipment. I'm not trying to charge the battery. I'm just trying to see, what I'm really trying to get at is, the gist of this experiment, the photoelectric experiment for one, is to find out either this work function, typically. I'm trying to learn something about this experiment, and this is the apparatus I use. See, by this technique, you can learn something about the material, because when this is part of your equipment, you just turn the voltage up, and at some point, the current will stop flowing. The current being an electron that can go from this emitted state, just being knocked out of the metal, comes out with a certain speed. Think of a bowl of little ping pong balls, and I throw in a ball, and I knock out a ping pong ball. But unless I want to know how fast the ping pong ball bounced out, how fast it was, well, what I could do is I could roll it up a plank. And as it rolls up the plank, depending on how high it rolls, I can tell how fast it came out of the bowl. Because unless I can't really measure the speed of the ping pong ball as it jumps out of the bowl, that's very hard to do. I mean, you have to have a very fast camera, high-speed camera to do that. But if I can make it roll up a plank, if I could see, it's much easier to see where it stops. And if I can know where it stops, it tells me how much potential energy it has at the top. And I go backwards and say, if I had that much potential energy, I must have had kinetic energy to start with. And that tells me the speed that I left the bowl. That's the experiment I'm doing. It means that it came across. This is actually a vacuum in here, by the way. There's a vacuum. Where's my apparatus here? Yeah, this is on the vacuum tube. I shine the electron light in on this surface. The electron pops out with a velocity that I don't know, but I want to know. If I can make it roll up a ramp or against that electric field, if it can make it across, it tells me it had enough kinetic energy to get across. When it stops getting across, that tells me that it didn't have enough, and it tells me the speed. That's a very good question. You have to know what you're looking for here, but you got the idea. It's a very illuminating question, actually. So that's the point. We're trying to find out the speed at which it pops out, which is hard to do. But if you can make it roll up a potential barrier, which the analogy being up a plank, an inclined plank, and you measure how high it goes, and you can sort of see when it stops, that tells you how much speed it had when it started up the plank. Does that make sense? Hopefully. Yes? Yes? Which line would that be there? This one? The yellow. Yeah, the yellow was too much voltage. That cut it off too soon. See, that would be, the yellow would be all the way over here. This is too much. So it way cut off the current. The electrons coming across with a certain total energy, and all became potential energy way inside. It never didn't come close to arriving here. So that would be the yellow. The one that is the cutoff is the one, hopefully, I need to get another color. Yeah, maybe this dashed line. That dashed line, that's the one when I got the battery voltage adjusted so that it has to climb just enough to stop the last electron from going. So that would be this dotted line here. That's when that cuts off. And that we call that the stopping, because that's the one where you exactly stopped it, just almost got there, but it didn't quite. The current goes to 0 at that point. This yellow line here? Oh yeah, that's too much. See, that voltage is too much. It stops the thing here, so it doesn't really tell you too much. The one that really tells you something is the one where it just cuts off the current from getting there. That tells you that I now have the voltage equal, when that happens, the yellow, oh no, the dotted one. The dotted one tells me that a half mv squared is equal to E times the dotted voltage. The dotted voltage. Because just there, the kinetic energy is all converted exactly into potential, and that's the stopping voltage. Because that just cuts the current off. That's this one here. Does that make some sense? So, but this is an example of a kind of potential barrier where the electron, so a very good analogy is to think of, again, I keep saying a ball rolling up and down a hill, which gets to the question here, how do we look at this? Well, the idea that we're working with is that if you have, you can have two conditions. One is a free electron, or free particle, which is not bound, where it has energy, a kinetic energy, above any of these retarding things. Even if there's a retarding potential, I can imagine a ball rolling along, and there's rolling along the ground, and there's an indentation in the ground. Okay, if the speed is high enough, the ball will just roll into the hole, and it'll roll right out. Now, quantum mechanically, speed is related to the inverse of the wavelength by the de Broglie relation, namely that the momentum, mv, is your v, is equal to h over lambda. So your v is inversely related. So the faster a thing is going, the shorter is its wavelength. So in a case like this, if I have a fast-moving ball, and it just comes to a indentation, and actually picks up speed, just think of a ball that's going to roll down, so it picks up speed, and then it rolls back up. So what's going to happen is it's got a long wavelength here, and suppose in here its wavelength is going to increase if it says higher speed, and when it rolls back out, its wavelength will increase like that. So but that's an unbound particle. That's free. It's got bumps in its life, but it's free. Yes, ma'am. Well, yeah. Oh, that's another failure of the diagram system that we use. What I should have is that I was drawing this here. I'm drawing sort of energy. So the total energy is constant, Yeah, it's a little tricky. The actual, physically, it's going to follow the contour. A ball rolling will follow the contour of the ground, right? So actually, geographically, it's going to do something like this. But if you take a potential energy, it's a long-winded story again. If you take a potential energy to be 0 here, it's going to lose potential energy going down, so its total energy will go up. Pardon me? It should gain kinetic energy. It's losing potential energy, gains kinetic energy, so it's actually speeding up. Yeah, in this case it does. It starts out with a certain amount of kinetic energy. This is telling you the kinetic energy increases. Potential energy is actually decreased because it's fallen, so it has less potential energy. And as it rolls back up, actually, I should have done it even better. This is a gradual change in the wavelength. The wavelength gets shorter, and then it gets shortest at the bottom, and it lengthens out again, and lengthens that way. That's right. I'm giving it some initial speed to start with. I'm going to give it, I do that. I mean, I just set the problem, I give it initial speed. If it went down into a hole, it would pick up speed as it went into the hole. It would pick up speed slowly, right? Just as this thing picks up speed slowly. It accelerates, speeds up, pardon? And then it would lose it coming out. As it rolls up, this thing loses speed as it goes up, right? It will lose speed. In fact, it's 0 at the top. So it picks up speed going to the bottom. It means the wavelength's going to get shorter. It reaches the bottom. It has enough kinetic energy. It's going to now start gaining potential energy. Its speed is going to decrease, so the wavelength will get longer until it reaches, and it gets out because it has enough energy to get out. See, right? And then, so the overall picture will look something like this as far as the wavelength goes. So it's actually going into the well, picks up speed, wavelength gets shorter, comes out of the well, and its wavelength gets longer. Okay? Yes, Renee, go ahead. Yes, but you see, the point is, for example, I could have started out with a problem like this, where I put the particle in the bottom of the well and give it a little speed. Then it's just going to rattle around in the bottom. That's too little. But if I give it more energy compared to the bottom, it's going to be, and then finally, I can give it enough energy that it's free. Right, it's relative to the well, if you will, no, it's weird, relative to the well. So relative to the well, this is quite a lot of energy. And it picks up kinetic, loses potential, and it can roll out of the well. Do these analogies help? I'm not sure. If we go on to this part here, the interesting point is, how do we extend that? Suppose let's see how we work this one out. One suggestion was potential is complicated as that. And now the situation has all the ingredients that we've dealt with so far. Namely, as Renee points out, it depends where the energy is compared to the bottom of the well. If the energy is way down here, you see, the energy is not enough to get you out of the well. So in this particular potential, and you want to make this infinitely high, as I recall? This one infinite, and that one is not infinite. Okay, so this has all the ingredients in it. You can have a shape of a box like that, and you put a particle in, and relative to the bottom, it has a certain amount of energy, so it kicks around at the bottom. Now, at this wall, that's infinite. So, okay, now we have various rules, namely that the number of waves, if you have a bound system, see, right now, first we talked about free. Now we're going to start talking about electrons that are also bound. Or they may be a little bit free, depending on the situation. If they're bound, then we always have the case where you have the lowest state has just sort of one half wavelength in it. We talked about that. Because what you're trying to do is again, because of this rule here, the lowest energy is where the wavelength is longest, then the V is smallest. So this is always the lowest energy state. Now the question is, there's a lot of things that go into this. Namely, this thing has to be a wave function such that psi squared is finite everywhere. Because you're going to try to do the integral of it over all space and get a finite number, because it's a probability, so it can't be infinite. So it has to be finite. So it has to do this nice quantization thing that Schrödinger pointed out. It has to fit into the box perfectly, or else, as that French demo showed you, if it doesn't come in just right, it does crazy things, and you can't normalize it. You can't get a finite answer. So the lowest state is always looking like that if it's bound, and the next step has more or less two half wavelengths in it. So looking at this problem, so that's one thing, is the order of states. Then you have the question of the boundaries of a bound state. And at an infinite wall, it goes to 0. The wave function goes to 0. Psi at an infinite wall is 0. And at a finite wall, namely like a ramp, it can sort of leak into the ramp a little bit. We call that kind of tunneling. So in a case like this, let's use these couple of rules. This is an infinite wall. The lowest state is 1/2 wavelength. And it hits the wall, and it can tunnel into the wall a little bit. But it must be 0 here. Let me call that distance here, x, and this maybe x equals L1, and maybe L2. Now, this is like a ramp and a flat table here. But this is a wall, a well, a ramp, and a table. And I just roll the ball in the bottom of this well, and this would be the first allowed state, quantized because I have to fit a half wave into just this space. And so it would have a shape like that. That make sense? And it's 0 here because it's infinite, just can't penetrate. And here it's finite, so it leaks a little bit. Now the second state, if there is one, it depends exactly where it is. But if I tell you that there is another state, this is E1, this is the ground state. E2 might look like this, but it necessarily has more wavelengths because it's a higher energy. So it's going to look something like this, and then it will leak. But it's got to be 0 here because this is infinite. This is side 2 at 0 is 0. And over here, I have to have the extra half wavelength. So these are my bound states. They're bound because their energy is not enough to get them out of the well. Yes, Renee? Yeah, there is a quantitative way of doing it. I haven't emphasized that. If you just say it tunnels or leaks, as far as we're concerned, it's good enough. What it depends on is how close this energy, which we don't really know is a complicated problem, how close it is to the escape energy. The closer you get to the escape energy, the more it tunnels. Until when you get above the escape energy, it just runs right out of the well. And that's the next step. Namely, in this particular kind of problem, you'll have a bound state, or two, or maybe more, depends on just the shape. But at some point, if the energy is up here, then we see that this particle can escape from the well because it has enough energy to here to sort of roll down, hit the wall, and come back out and roll back out of the well. So in a case like that, the picture is going to look something like this. It will be 0 here. Well, let's start with it here. Here, you see, this is, again, the potential energy. If this is the total energy, the same kind of example here, this is the potential, this is the kinetic energy. See, this is its total energy, and this is the potential energy. Sort of the same argument as I used here. This is the potential energy, this is total, this is potential, the difference is kinetic. So this is the potential energy, U, in this particular region, this level. Now, as I go along, it's the same argument here. Just how I make this, I'm not telling you, but let's say it looks like this. As my particle moves along, it has its own total energy. The kinetic energy is the difference here. So the kinetic energy actually, as you see, increases. Right? Let me make the kinetic energy yellow. So as you would expect, as the thing rolls down the hill, its kinetic energy increases, and increases further. And it increases, and here's where its kinetic energy, because it's the difference between the potential energy and the total energy. So those are my kinetic energies. Okay, and how I represent that as a wave function is, okay, let me continue using yellow chalk. Namely, this is telling me that I have a lot of kinetic energy. A lot of kinetic energy means a high speed. High speed means short wavelength, so that in this part of the space, the wave function has a high kinetic energy, high velocity, short wavelength. But when it reaches this point, the infinite barrier, it must be 0. So what I have is a short wavelength up to here. See, up to here, they're all the same kinetic energy. So the wavelength is the same. And when I reach this point, it starts to lose kinetic energy, so the wavelength must get longer. Longer, 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 because I see the kinetic energy is decreasing. Longer yet, and then it gets, once I reach here, it's looking like that, because it's really slow once it comes out there. Yes? Why have your elements are more radioactive? I'm not sure that it does. I think partly they're more radioactive. That's a hard question. I think it has to do somehow, you know, if you take, for example, a light element like carbon, it has some isotopes that are radioactive. And they just have the wrong number of neutrons and protons ratio, and there are energy levels within there that are not so stable, and so that they're happier if they shoot out, say, a neutron or something and change to some more stable state. That's a very more complicated question. But I was just trying to show you here how, if you have a complicated potential, and once you get over here, you see you do get a little leakage. Well, no, if you're a free electron like this, you'll just ride in, you'll bump the wall, and you'll roll out. You'll speed up, and as you roll back out, you'll slow down, and it shows up here. And, and the other thing that you should do, and that's the amplitude. I forgot about that, folks. But because it's slowing down, the amplitude actually gets larger, because if it's going slower, you're more likely to be able to catch it. So the amplitude gets larger. Oh, that's the third aspect. So you have 3 aspects. So you have how many lobes it has, and the number of lobes depends on how fast it's going. So here it's going fast, so it has a lot of lobes, very wiggly. Over here it's slowing down, the number of lobes decreases. But because it's going slower, you also can catch it more readily, and the amplitude increases, and so it looks something like that. That's the actual picture. And I hope that answers is better. Yes, dear, comment. Is there what? Bound states? Ah, you mean between here and here? No, these bound states, these are your quantum levels. So that if you were to ever measure, for example, the